Hello, welcome to Golden Droplets, a mini-series of webinars aimed to reduce the distance between the academy and the industry. In today's episode, number 42, we will try to answer one question. Would Sherlock Holmes be a good geologist? Well, let's ask him. You are asking me if I could be a good geologist? Let me see. Yes, of course. My deductive methods, my ethics of working, the fact that I read a lot and I study a lot and I try to figure out the links between things. Yes, I think I could have been a good geologist. Thank you for asking. The efficiency of a field geologist depends on his or her capability of observation. I can't explain how I miss it, said the inspector with expression of nonsense. It was invisible because it was buried in the mud. If I discovered it, was because I was looking for it. The correct observation of a phenomenon contributes to its better understanding and allows a more rational and effective orientation of the investigation. This is why it's so important to master the steps that guarantee a correct observation of any phenomenon. There are basically 3 steps to achieve a correct observation. The first one is the perception of the object. The second is the primary observation or first impression. And third, the elaboration of a plan for the description of the phenomenon. So how can I achieve a correct observation? Observation is the basis of all empiric procedures and is the most elemental form of the scientific knowledge. There isn't any specialty or branch of the science where measurements, descriptions, or observations in the broad sense of the word are not carried out. The correct observation of a phenomenon contributes to its better comprehension, also allowing a more rational and effective orientation of the investigation. But the height of the murderer, how could you find out if we have never seen the man? Dear Watson, you saw me doing measurements in the room. The distance between 2 footsteps showed me clearly the size of our man. A scientific observation not only should supply information about the investigated object, but it also must provoke the formulation of new problem, or should reveal new facets of the same problem. So, number 1, the correct observation contributes to a better comprehension. A scientific observation should supply information about the object, but also create new questions. Very important is point number 3. Observation is an interpretative and cyclical process. It is also very important that the geologist will have an initial idea about the process that he is studying before beginning his analysis. His objective will be to disprove such hypothesis. If we cannot disprove the hypothesis, then we have a theory to work with. So measurements, we have 2 kinds of basic measurements. One is the search for experimental errors, and the second one is a synthesis of the information. I will not talk here about quality controls and other subjects that I have treated in previous episodes. We are concentrating on the most basic of these measurements. First measurement is the measurement of the systematic error of our data. And there is the formula that we can use to determine if we have a systematic error or not. And then this is the formula that we use to find out if we have a causal error. Now, if the error that we determine here had a value between 0.95 and 1.5, we can assume that there isn't a systematic error of our data, and we can go directly to calculate the causal error. Otherwise, we need to first eliminate this error by subtracting the systematic error, this value here, from each of our data. This is a process similar to how topography close a polygon. when they got to the end of the polygon, if they have an error, they take that error and eliminate that error from each point. That way they close the polygon that they are mapping. For quantitative analysis, if the value of the causal error is superior to 1.6, then we cannot rely on the quality of the data. We really need to redo the assaying, redo the experiment, etc. For qualitative or semi-quantitative analysis, well, that limit should be 3. But if you get any value above that, we cannot work with that data. Then it comes the synthesis of the information. And we are talking here about, for example, the construction of histograms and polygons of frequency, and the statistic pre-elaboration of the measurements. The histograms and polygon of frequency are an excellent tool. They help us. First of all, they are very easy to construct, very fast, and they give us a lot of statistical information like the presence of outlier, the value of the modes, the median, the average, etc. Common steps of the elaboration of the data include first the detection and processing of statistical outliers and of the stream values of the study sample. And for that, there are several methods like the formula median plus minus 4 times the standard deviation. But as I mentioned before, with an histogram, it is very simple and easy, direct to figure out which values are outside, are outliers and need to be dealt with. Now, if you have enough data, you can just delete those outliers. If you don't have enough data, let's say you're only working with 30, 50 samples, you take that stream value and substitute by the value of the mean determined using that stream value. Then an optional step is the transformation of the data to 100% or any other of the methods like the compositional data analysis, which is not optional. If you're going to be doing correlation analysis, that is mandatory, you need to do it. But sometimes you just want to convert all your data to a range from 0 to 100%. Then we have the determination of the distribution law, usually by the method of Kashdan, which determine the asymmetry and the excess. If any of those two parameters will have a value above 3, we consider the distribution law as log normal, determine the logarithms of all the data for that element. And then the determination of the median and the relative and absolute modes, we do that with the histogram. Then we determine the mean, the standard deviation, the variability coefficient, the confidence intervals, etc., and the determination of the levels of anomaly. These are not all the possible variables to be calculated, but this is sufficient to get a first idea of the statistics of your data. The use of tables and comparative graphic is very recommendable. Then we need to start working on the systematization of the information. "Dear Watson," said Holmes, approaching his incredibly detailed and orderly, "I'm sure that we will find a reference to that type of letter in this file." When you have a situation where you know very well all the variables, it is recommended to use a codified system to do the logging. This codified information has obvious advantages, like it guarantees a uniform observation of the essential parameters of the phenomenon, and it reduces the subjective factor of the obtained information. Also, when you have several teams working in the field, you guarantee that every team will go through the same steps in the descriptions. The codified information is easy to understand, to process, to regroup and study, and also to translate, and it will influence very positively in the final quality of the observation and in the speed of its interpretation. Codified systems are not difficult to create. First, you just need to put in a paper all the parameters that you want to observe. And of course, don't forget to include others because sometimes we don't know enough to know the totality of the parameters that we're going to find in the field. And next, we order these parameters in a logical way. We number them, and we use card, like for example, 3 by 5 inches. At the center of each card and its back, it remains free for irregular descriptions, and we will use the edge of the card to codify the information. We will be interested in more details about this. There will be a reference at the end of this presentation with the description of how to create these cards. But just as an example, I want to show you here 2 different codified cards. The card from the left is a very simple card that we created when we are working with non-technical personnel. So we have workers, they know how to read and write, and they have a minimum knowledge. They are not professionals, but they can use these cards to fill a lot of information from the sampling. Here to the right, this is a more professional codified card. As I said, this one is a card for soil sampling, and you have the back of the card to make drawings or put something that you miss. But each of these numbers correspond to a parameter that we're going to be describing, like the location of the project, the type of relief, the depth of the sampling, the type of composition of the sample, everything. You can put all that information into a 3 by 5 inches card that you can carry in your pocket. This is a very useful way. And then you can put all this information into a database using Microsoft Access or something similar. Now, talking about the systematization of the information, a good primary documentation must fulfill the following conditions. First, uniformity. This is represented by the same investigator, the same analytical equipment, the same technology, etc., etc., etc. Even when you have different investigators, well, you have a similar way to describe this process or the work that is being done. This is done with the codified cards. This is a great help to this. Precision. We need to have all the statistical treatment, the experimental designs, etc. Everything must be completed to the same degree of precision. Reproducibility, and this is one of the most important ones. Sometimes you process some data, and you got results, and you put, you presented, blah, 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 you put it back in your filing cabinet, and a month after, somebody comes in and asks you, hey, how did you got this result? And if you don't have a system that you can show them to reproduce all your steps, then you are in a big problem, because most probably you are working on a different project now, and you forgot all about that previous one. So your system must have the capability of being reproducible. And finally, the document must be easy access, and it must be readable. The access, we now have the cloud. We can use Dropbox, Google Drive. I mean, any of the cloud systems will be useful to grant an easy access to your data. And readability means that it should be, if it is handwritten, it should be in legible letters. Talking a little bit more about the reproducibility, those of you that have been in previous courses have seen this Excel format that I use. Many people use the computer language R, which is very good for this, because every step that you do, it keeps a record. But R is not very user-friendly. You can get the same result using Excel and creating a slide for each of the steps that you are doing. And here on the first table, you have an indexed table, a table of content that you can quickly jump to where you want to go. So, conclusions and some recommendations. Given the importance of a correct observation for the verification of any hypothesis and for the development of scientific ideas, it is necessary to pay attention to the collection and conservation of the primary documentation. Remember that before beginning any observation, you need to have an hypothesis, an idea, and your work will be oriented to test that hypothesis. Not only to test, you need to try to disprove your hypothesis. You need to try to prove that you are wrong. If you cannot prove that, then you can work with that hypothesis. Because of that, the observation must be selective and interpretative at the same time in order to become scientific. And don't tie yourself to a hypothesis. I mean, the hypothesis must adapt to the facts and not the other way around. There is a system also of investigations called tabula rasa, when they confront the problem without any preconceived idea. That is why it's called tabula rasa. And then it collects information until he can formulate an hypothesis. This is a way of doing science. It's not wrong, but it's not effective in geology. In geology, it's much more effective to have an idea, to figure out what will be the most important aspect or test that I can do to prove me wrong. And if I cannot prove me wrong, then that will be the hypothesis that I will be using. Now, since observation by themselves, they're usually not enough, we always need to do some statistical processing of the data. Especially we are going to be using artificial intelligence or machine learning that allow us to get results that normal statistical method will not get us there. The methods proposed here in this little presentation are enough for a preliminary elaboration of any assemblage of geological measurements. If you apply these recommendations, plus a constant search of improvement based on the comparison and critical analysis of previous observation, you will soon improve the quality of your own observations. Again, we recommend the codification as a way of establishing a unity and a reproducibility of the results. So answering our first question, yes, we think Sherlock Holmes would have been a great geologist. Well, until next time, goodbye.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.